Hello students. In this video, we shall be covering topics under work and energy. Work and energy is one of the most important topics in physics, and the definition of work you will get to know is slightly different from what we ideally refer to in everyday life. For example, when you're sitting and reading a book or listening to music or even watching TV, under normal circumstances, we would refer to all such activities as work. But work in physics is defined in an entirely different way. In today's session, we shall learn about work, its definition and formulae, and the topics that shall be covered are: as mentioned earlier, the scientific definition of work is slightly different from the everyday concept of work that we refer to. Let's consider another example. Think of a man standing in a bus stand with a bag in his hand. Ideally, if he is standing for quite a few minutes, we would say that he has been doing a lot of work. However, this concept of work is not applicable in physics. In physics, work is only done when there is a displacement. Here, we see that the man standing at the bus stand, waiting for the bus, does not move from his current position. So, displacement is zero, and therefore, work done is also zero. Now, when the bus arrives, the man runs towards the bus to catch it. There is a displacement over a certain distance till the man is able to board the bus. And according to physics, we would now say that work has been done by the man. To calculate work done, force applied needs to be in the direction of displacement. So, in this example, if force applied by the man to catch the bus is 20 newtons and displacement is 5 meters, then work done is 100 joules. Remember that 1 joule of work would simply be 1 newton times 1 meter. So, when 1 newton force is applied on an object such that its displacement is 1 meter in the direction of force, then work done is 1 joule. Another important thing to remember is that although work is a product of two vector quantities, work itself is a scalar. It only has a magnitude, and direction is not relevant in case of work. So, as we have learned a few things about work, we need to also remember that to calculate work done, force applied needs to be in the direction of displacement. Otherwise, the calculation of work done would be different. For example, let's consider a man pulling a cart. Work done in this case is simple, as displacement of the cart is in the direction of the man pulling the cart. So, work will be equal to the force applied by the man times displacement of the cart. Now, let us shift over to the topic of energy from work. So, tell me, what do you understand about energy? We talk about energy when we need to do different kinds of work. Energy is therefore the capability of an individual to do work. It is simple. If we have more energy, we can do more work. A man riding a bicycle for long hours gets tired after a while. This is because of loss of energy. Energy is not just relevant in the case of human beings. It is required in all kinds of work, such as electrical energy that runs fans, air conditioners, wind energy, and thermal energy. Car and automobiles run on petrol and diesel as fuels. Sun is one of the biggest sources of energy. It is called solar energy. There are two principal sources of energy: renewable and non-renewable. Energy is always transformed from one form to another. It is never created. The two terms that we generally talk about in terms of energy are potential and kinetic energy. Potential energy is basically the stored form of energy. So, potential energy is stored in bodies when it is at rest. When a body starts moving, this energy gets converted into kinetic energy. Total energy of the system remains constant, and this is called the law of conservation of energy. By the law of conservation of energy, it is only the form of energy that changes. the total energy remains constant. The formula to calculate potential energy is mgh, where m stands for the mass of the object, g is for acceleration due to gravity, and h is the height of the object. So, potential energy is energy stored in the object due to its position. Alternatively, kinetic energy is equal to half of mv squared. It is energy possessed by a body by virtue of its motion. Let's look at the example of a pendulum. When we hold the pendulum on one side, potential energy is generated, and when we release it, potential energy gets converted into kinetic energy and back to potential energy, and so on and so forth. At the two extremes, velocity is equal to 0, and hence there is no kinetic energy. Only potential energy exists. Let's look at an example and calculate potential energy of a 78 kg man standing on a tower that is 32 meters high. If the man had jumped off the tower, he would have converted all of potential energy into kinetic energy at the bottom of the tower. But this is not a very good example to discuss, and so we will look at an example of a man throwing a ball. When a man throws a ball at a speed of 9 meters per second that weighs 0.145 kgs, then kinetic energy generated is half mv squared and can be calculated to be 5.9 joules. Now, let us look at an example of how energy is converted from one form to another while falling from a height. Initially, let's consider that the total energy conserved in the ball is 20 joules. Since there is no velocity of the ball at the top before being released, kinetic energy is equal to 0. Thus, at the first point, total energy is only conserved in the form of potential energy, which is 20 joules. In the second stage, when the ball starts falling, the height of the ball starts decreasing, resulting in the reduction of potential energy. And that reduction in energy form gets converted to kinetic energy. So, here we see that potential energy falls to 15 joules and kinetic energy increases to 5 joules. The fall in potential energy and rise in kinetic energy continues as the ball loses height and gains velocity respectively. At the last point where the ball hits the ground, potential energy gets totally converted to kinetic energy, and total energy is equal to total kinetic energy. Potential energy is converted to 0 as height is equal to 0. So this section teaches us about the two principal forms of energy: energy at rest, potential energy, and in motion, kinetic energy, that changes forms according to the state of bodies. But as we learn about energy, we also need to know that not everyone can have the same capacity to do work. An old man can row a boat at a slower rate than a younger, fitter person. So capacity to do work in physics is referred to as power. The rate of work or amount of work done in a certain period of time is called power. In terms of energy, power is defined as energy consumed per unit time. So, it is also referred to as the rate of energy consumed. In the 18th century, James Watt had defined power for steam engines, making use of a much higher unit of power called horsepower. 1 horsepower is equal to 746 watts. Power is also used to measure the consumption of energy in machinery and automobiles. The energy consumed in 1 hour is the numerical value of power expressed in kilowatt hour. Expression of kilowatt hour in terms of joules is expressed in the following way. All meters at home use the value of kilowatt hour as a unit to express electrical energy used. Kilowatt hour is also written in bulbs that you purchase, so that you know how much energy it would consume. So let us calculate power from an example. Here the mass of the body is given as 10 kgs. So we calculate the weight from mass. Given the number of staircases to climb, we need to find the height climbed in meter value. Thereafter, power is calculated and the result is 25 watts. So this brings us to the end of the session on work, energy and power. We wish you all the energy and power so you can do a lot of work. Goodbye.